Hello and happy Friday. We are going to round out this week's topics within Unit 5 by talking about reaction half-life, which is a very specific type of integrated rate law, and one with which I think you probably have some familiarity. And by the end of today's lesson, you should be able to say that I can relate the half-life of a first-order reaction to the concentration of reactants, the rate constant, and time. So let's continue on with our usual. Do a little warm up today. So look at the three graphs at the top of the screen. Based on this data, what is the reaction order, the decomposition of nitrogen dioxide? All of these are different graphs related to the decomposition of nitrogen dioxide. Hopefully, you're easily able to identify this one as a second order reaction. And we know it's a second order reaction because the inverse of the concentration graph is the one that is a straight line. Remember, we need to look for a straight line in our integrated rate laws. Integrated rate law lines. That is the one that's going to tell us which order it is. So, second order for the decomposition of nitrogen dioxide. And with that, let's get started talking about reaction half-life. So, you do already know about half-life's radioactive decay. That's exactly what we're talking about right here. So it is the time required for the concentration of the reactant to reach half of its initial value. All of this makes sense when you think about what exactly you're saying when you say half-life. It's the life of an amount of a material for it, or the life or the time it takes for that amount to become half of its starting value. When talking about half-lives, we use appropriate units of time that can mean anything from seconds to hours to days to years to hundreds of millions of years. It all depends on what substance it is that we're talking about. Depending on what units of time we use to describe the time for the half-life, we may need to do some converting in order to relate that back to rate constants and rate laws, but the half-life is always described in the appropriate units of time. Most radioactive decay reactions, at least, are first order reactions, so that's going to be the focus of what we talk about today. And they are constant at fixed conditions. So that means that if the half-life of some substance is 20 minutes, as long as the conditions don't change, it will be, if you start off with 100 grams, after 20 minutes, you'll have 50 grams. And then after another 20 minutes, you'll have 25 grams. And after another 20 minutes, you'll have 12.5 grams, and so on and so forth. The starting concentration does not drive at all the rate of decomposition. For some second order reactions, second order half-lives, the starting composition, or the starting concentration does matter. So we're focusing on first order half-life reactions, and we're going to plug that information right in and start talking about formulas. So this formula should look very familiar because it is the integrated rate law for a first order reaction. We've got the natural log of the concentration of A, 0 over the concentration of A sub T is equal to the rate constant times time. This is something we talked a lot about yesterday. Should look very familiar. When we're talking about a half-life, though, we're talking about a very specific version of this, this rate law. And so we're going to have to keep in mind a few things. Our t, we're going to call it the t sub 1/2 because it is the time to the half-life, so the time at which half has decayed or disappeared. With that in mind, we know that the concentration of A at time t is going to be half of the concentration of A at time 0 because A at time 0 is the initial concentration of substance A. So thereby, we understand that the concentration of A at time t, or in this case, A that time t is going to be the half-life time. It's going to be half the concentration, half the value of the concentration of A at time 0. So when we think about that information and we plug all of that back into our initial initial integrated rate law equation, it's going to look something like this. We've got our natural log of the initial concentration of A divided by 1/2 the initial concentration of A is equal to the rate constant times t. We can cancel out our initial concentrations of A because they're exactly the same, can we not? And because 1/2 is in the denominator, it means that we will flip that bad boy, and that's why we end up with 2. So we cancel out our initial concentrations of substance A, and we flip our 1/2 to equal 2. So we have the natural log of 2 is equal to the rate constant times the half-life time. And we can actually simplify that further because we can find the natural log of 2, and we can solve for time. So we can use our rate constant to find the half-life, because if we take the natural log of 2 divided by the rate constant, or 0.693 divided by the rate constant, we can find the time of the half-life. So how long it takes for what substance to decay to half of its original size, or its original amount. And so that natural log of 2, 0.693 divided by K, that is going to be a very important formula to remember. The half-life time, T sub 1/2, is equal to 0.693 divided by the rate constant. Let's plug that in with a practice problem. So iodine 123 is used to study thyroid gland function. So it'd be something that you would ingest, or would be injected in a medical procedure to help a doctor study your thyroid function and possibly ascertain hyper or hypothyroidism. And this radioactive isotope breaks down in a first order process, no surprise there, with a half-life of 13.1 hours. What is the rate constant for the process? So, should not be too terribly complicated or daunting, because we just talked about how we relate the half-life time and the natural log of 2 is 0.693 divided by the rate constant. Here, we're looking for the rate constant, and we know the half-life time. So if we take our original equation and we just flip this around so that we can find our rate constant instead of the half-life, because we already know our half-life, we're going to have something that looks like that. Rate constant is equal to the natural log of 2, or 0.693 divided by the half-life. And then we just plug our numbers in. Or do we? No, we have to convert our hours into seconds, because remember, our rate constant, our K, has some pretty specific units. Hopefully you remember what those units are. So first, let's convert our time into minutes, pardon, not minutes, seconds. I'm going to say 13.1 hours times 60 minutes times 60 seconds for 47,160 seconds. And then we're going to plug that into our equation to find our rate constant. So K equals 0.693 divided by 47,160, which equals 1.47 times 10 to the negative fifth per second, or s to the negative first. And 1 over s, or s to the negative first, remember, is our unit for a first order reaction. So there you have it. Not terribly complicated. Something related to probably a lot of information that you're already at least generally familiar with regarding radioactive decay. And now you've been able to relate radioactive decay to rate laws, specifically first order rate laws, and then integrating those first order rate laws. And now you've got something pretty useful out of that. So once again, if you have any questions, feel free to send me an email. Otherwise, have a very good weekend.